Good day, everyone. We are the group 5. I am Alin Dave Salisi together with my group mate John Christopher Manes and Emil Christian Sanchez. So we are here to discuss about tension testing. So basically, material testing is a respected and established technique that is used to ascertain both the physical and mechanical properties of raw materials and components. It can be used to examine almost anything from human hair to steel, ceramics, and composite materials. Tension testing is a type of destructive testing that includes methods where your material is broken down in order to determine mechanical properties such as strength, toughness, and hardness. The benefits of destructive testing is that it verifies properties of metal, it determines quality of welds, it helps you reduce failures, accidents, and cost, and finally, it ensures compliance with regulations. Tension testing is a way of determining how something will react when it is pulled apart when a force is applied to it in tension. And it is one of the simplest and most widely used mechanical tests by measuring the force required to elongate a specimen to breaking point. Material properties can be determined that will allow designers and quality managers to predict how materials and products of behave in the intent application. The picture shows the typical tensile test specimen. A gauge length, it corresponds to the effective length of the specimen over which the elongation occurs. The gauge length is the reference length used in elongations calculations depending on the test standard. The gauge length is either 2 inches, 80 millimeters, or 50 millimeters. Multiplying the width and the thickness within the gauge length determines the initial cross-sectional area before testing. So the suggested formula for the determination of gauge length is shows above, depending on the initial cross-sectional area of the specimen, or the AO, where K is 11.3 for relatively long bars, and for relatively short bars is K is 565. In tensile testing of metals and polymers, an elastic deformations at a certain limit is observed first, which is followed by considerable plastic or permanent deformation. The plastic deformations ends with a total fractures of the specimen. In ceramic and some plastic, very little deformations is observed because atoms behave most likely either positive or negative ions and are bound by Coulomb forces between them, and they are usually combinations of metals or semiconductors with oxygen, nitrogen, and carbon. The first set of materials of which can be plastically deformed are called ductile, while brittle is the second set of materials that are plastically deformed. The picture shows the stress strain curve for a typical low carbon steel. A stress strain curve is a graphical way to show the reaction of a material when a load is applied. It shows a comparison between stress and strain. Stress is the ratio of the load or force to the cross-sectional area of the material to which the load is applied. Stress is proportional to strain in the elastic range from point A to point B, and the proportionality constant is Young's modulus. Thus, stress is equal to Young's modulus over spring constant times strain. Elastic range is the limit of strains produced in the material up to which original shape of the material can be restored is considered as elastic range. On application of force in an elastic range, material restores its shapes once the force is removed. Stress strain curve yield point is the material property defined as the stress at which a material begins to deform plastically. Prior to the yield point, the material will deform elastically and will return to its original shape when the applied stress is removed. Once the yield point is passed, some fraction of the deformation will be permanent and non-reversible. The yield point determines the limits of performance for mechanical components since it represents the upper limit to the forces that can be applied without permanent deformation. The mechanical strength of the material corresponding to yield point is defined as the yield strength. The table shows the elastic moduli of some common engineering materials. The materials are the alloys, copper, nickel, low-C steel, stainless steel, titanium, and tungsten. The alloy is composed of elastic modulus AgPH 72.4 and copper 110, nickel 207, low-C steel 200, stainless steel 193, titanium 117, and tungsten 400. Yield strength refers to an indication of a maximum stress that can be developed in a material without causing plastic deformation. It is the stress at which a material exhibits a specified permanent deformation and is a practical approximation of the elastic limit. Upper yield strength is the maximum stress reached in the specimen prior to the onset of significant plastic deformation, while the lower yield strength is that it is the stress corresponding to the horizontal portion of the stress strain curve immediately following the beginning of plastic deformation. Thus, this serrated yielding, it is the oscillating character of the portion of the stress strain curve that represents temporary plastic inability.
Toughness is the ability of the material to absorb mechanical energy until fracture. Can be defined as the strain integral of the stress strain curve. It is the area under the stress strain curve until the fracture strain. And toughness is the resistance to shock. So we all know that to get the area under the curve, we must use an integral. So toughness is the integral of the stress evaluated from 0 to strain. So here on the next slide is some of the materials with their ultimate strength and the modulus of toughness. You can pause the video to observe it or analyze it. So next is the resilience. It is the ability to absorb energy solely in the elastic region. Modulus of resilience, the quantitative amount of energy per unit volume which the material will possess when subjected to the elastic limit stress. Ductility is the quality of a material by virtue that it can be plastically elongated. So next is the plastic range. As one of the load specimen beyond the yield point and then relaxes the load to zero, the material does not recover its original dimensions completely. Instead, a permanent strain is observed. So, for example, in a rubber band, when you stretch it, fully without breaking it, uh, when you release it, it will not go back to its original round shape, and it will become elongated. So this property characterizes the induced deformation as plastic, and the portion of the stress strain curve beyond yield point is termed as the plastic. Next is the ultimate tensile strength, or UTS, is the maximum point in the engineering stress strain curve. Ultimate tensile strength can be called shortly as tensile strength. So it is the maximum amount of load that or stress that the material can handle before breaking. Next is the necking. Necking is defined as a localized decrease in the cross-sectional area of the specimen which results due to the imperfections which act as local stress traces in the material. So as you can see, the ultimate strength is at the point where necking occurs. So equipment for tensile testing. So most commonly known as a universal testing machine. So the most common testing machine used in tensile testing is called the universal testing machine. This type of machine has two crossheads. One is adjusted for the length of the specimen and the other is driven to apply tension to the test specimen. So there are two types of testing machine: hydraulic powered and electromagnetically powered. The machine must have four main parameters: the force capacity, speed, precision, and accuracy. So, force capacity. This refers to the fact that the machine must be able to generate enough force to fracture the specimen. So, if you have a harder material, then you need a machine that has a much more greater force capacity. So, speed. The machine must be able to apply the force quickly or slowly enough to properly mimic the actual application. So, precision and accuracy. The machine must be able to accurately and precisely measure the gauge length and force applied. So, Next is the process. The test process involves placing the test specimen in the testing machine and slowly extending it until it fractures. During this process, the elongation of the gauge section is recorded against the applied force. The data is manipulated so it's not specific to the geometry of the test sample. The measurement is used to calculate the engineering strain. So we all know that the stress is the ratio of the applied load to the cross-sectional area. So applied load de- denoted by P and the cross-sectional area is denoted by A sub 0.
Compression test is used to measure the capacity of material to withstand loads tending to reduce size. It is opposite to tensile strength, which withstands loads tending to elongate. If tension test is to elongate the material, compression test is to compress the material. Gray cast iron and concrete are the materials that can be tested in compression test. As what you can see in the graph, these materials are more compatible to compress than to elongate because they have more compression than tension. So this is an example of equipments used for compression testing. The steel drum is undergoing compression test as shown in the figure. This is also an example for compression testing where the corrugated box is being compressed by the compression test machine. Hydraulic press can also be used for compression testing. Compressive strength is often measured on a universal testing machine. These range from very small tabletop systems to ones with over 53 meganewton capacity. Measurements of compressive strength are affected by the specific test method and conditions of measurement. When a specimen of material is loaded in such a way that it extends, it is said to be in tension. On the other hand, if the material compresses and shortens, it is in compression. The apparatus used for tensile and compressive test is the same. However, in a compressive test, rather than applying uniaxial tensile load, an uniaxial compressive load is applied. Brittle materials like cast iron and concrete are often weak in tension because of the presence of submicroscopic cracks and faults. However, these materials are quite strong in compression due to the fact that compression test tends to increase the cross-sectional area of specimens, preventing necking to occur. In general, the average compressive strength to tensile strength ratio of brittle materials is around 8:1. Wood is commonly used in engineering material that does not show brittle characteristics under tensile loading and considerably stronger in tension than in compression. This is because the cell structure in the material are stronger in the longitudinal than transverse direction. Compression fractures include those which are caused by buckling, bending due to pressure, heat, etc., and shearing, cutting off on a certain angle. For design purposes, the compressive strength value is restricted by dividing with a factor of safety whose value depends on the design philosophy used. And that will be all. Thank you.